Good day everyone. In this video you will learn how to do circuit analysis using Phasor. You will go through two examples. The first example is on KVL and the final example is on nodal analysis. Before we proceed, let us recap on two terminologies that you should be familiar with by this time, which is on the impedance and the admittance, which are actually equivalent to resistance and conductance in the resistive circuit. Therefore, all the basic laws and theorems related to linear resistive circuits are applicable in Phasor form. Just that you have to use complex algebra. Example 1 is on KVL. But before that, since the KVL concept is used in mesh analysis, therefore I will not show the examples on mesh analysis. In this example, you need to find the steady state current I using Phasor for the RLC circuit in figure E1. So let us see how to solve this circuit. Okay, so the first step, draw the circuit, but in this case it should be in Phasor form. This is our original circuit in time domain. So you need to draw the circuit in Phasor form. This is the circuit. So if you notice, we use the capital letter to indicate the Phasor value. This is the Phasor value for our voltage source. And similarly, the current that we want to find, we also need to change the label by using capital letter I. So how do we get the value of this? So we have a sine wave of 100 cosine 100t, our time domain voltage value. So we change it to Phasor form is equivalent to 100, the magnitude, and the angle of 0 degree. In the case of impedance, okay, for the resistor, it remains the same, which is equivalent to 6 ohm. For the inductor, okay, so the reactance value is equivalent to J omega L, which is equivalent to J 4 ohms. For the capacitor, is equivalent to 1 over J omega C. After you substitute the value, then you will get minus 10 J ohms. So once we have drawn the circuit, now we can analyze it. So in this case, we will use Kirchhoff voltage law. The Kirchhoff voltage law states that the total voltage in a closed loop is equivalent to 0. We have the voltage across resistor plus voltage across inductor, and a voltage across capacitor is equivalent to the voltage of the source. So we have these expressions of KVL. So we substitute the value inside this. So we have this in the polar form, and the bottom part is in the rectangular form. So in this case, we have to change the bottom part to the polar form. So we get these expressions over here. And then we can solve this algebraically. Multiplications. Okay, we have 10 over with 10 square root 2 over with the 6 times 2. And then the angle is 0 minus, in this case it will become plus 45 degree. So we change to the polar form, get the steady state value straight away as indicated by this. So we get the current expression in time domain is equivalent to 1.179 cosine of 100t plus 45 degree ampere. So it's quite simple when we use the Phasor form. Now we will see our final example, which is on nodal analysis. In this example, you need to find VA when you have two different current sources acting on it, which is current I1 and current I2. Since there are two different sources acting on the circuit, so we need to figure out the omega value first. So we need to compare the omega of two different sources that we have. So if we have a different omega, in this case you must use superposition theorem to solve the problem. Whereas if you have the same omega, then you can use any method that is suitable or which is the one that is easier for you to get the solution. Okay, since in this case both of our sources are using the same having the same omega value, which is equivalent to 100 radian per second, so we can choose any suitable method to get our results. Okay, but because of the circuit that we have over here, so the most suitable one is the nodal analysis. We need to draw the circuit in Phasor form. This is our circuit in time domain, this one. So we have to change the value into Phasor. So the current I1, okay, notice we use the capital letter to indicate the Phasor. Similarly, in the case of voltage that we want to determine, VA, and because we are using the analysis, so I straight away label the other node as VB. And the other things that you have to change is the impedance value. For the resistor, it still remain the same as it is. Whereas for the capacitor, so you have to use 1 over j omega c to get this. And then for the inductor, you need to use j omega L to get this value. So this is how we do the transformation for the current source. We have this I1. So the Phasor value for I1 is, you have the magnitude of 1 and the angle is 0 degree. Whereas for the I2, so you have the magnitude of 0.5 and then the angle of minus 90 degree. Whereas for the impedance, as I mentioned before this, for the inductor, it will become minus J4 when you substitute the value. For the capacitors, depends on the capacitance value. For the one with 1 millifarad, you will get is equivalent to the minus J10 ohms. The one with the 5 millifarad, you will get is equivalent to minus 2 J ohms. Now we can apply the nodal analysis to our circuit. So first we apply KCL at node A. So we have the expression where the current flowing out of the node is given by VA minus ground over 4 minus J2 plus the expression of current of this branch. So we have VA minus VB over with minus J10 is equivalent to the current flowing into the node, which is from our source 1, is equivalent to 1 angle of 0. We apply the conjugate, apply top and bottom with the conjugate value. The final expression is equivalent to VA open bracket 4 plus J2 close bracket over with the 20. And don't forget that J squared is equivalent to minus 1. So that's why if you look at the bottom part, you have 16 plus 4, so it will give you 20, and then the imaginary value is cancelled off. Final expression, node A is equivalent to this, and we call this as equation 1. Next, we'll apply the KCL for node B. So in this case, we consider all the current flowing out of the node. So the first part for this branch, so you have VB minus VA over with minus J10. And then for the next branch, this, so you have VB minus ground, which is 0, over with 2 plus J4, the resistor is in series with the inductor, plus with the current from the source I2, which is equivalent to 0.5 minus angle of 90 degree is equivalent to 0. We apply the conjugate top and bottom. So in this case, because we have plus, so we have to apply top and bottom with 2 minus J4. We expand the multiplications, and finally we will get this VA open bracket 2 minus J4 close bracket over with the 4 minus 1 times 16, so you will get 20, same as previous. So when you solve for this, so you will get final expression is equivalent to VB multiply with the 2 minus J2 minus with the J2 VA plus 10 magnitude with the angle of minus 90 degree is equivalent to 0, and we call this as equation 2. So we have already two equations that we can solve to get the solution. In this example, because we are only interested to find the value of VA, therefore from equation 1, we rearrange it so that we get the expressions of VB in terms of VA, and we call this as equation 1A. Next, we substitute equation 1A into equation 2. Solve this complex number, so you will get the final value is equivalent to 1 minus J2 in rectangular form. So always remember you have to change it to the polar form if you want to obtain the steady state value which is in the time domain. So you will get the value of square root 5 for the magnitude and the angle of minus 63.4 volt. Final step is change the phasor value into the time domain. A in time domain is equivalent to square root 5 cosine of 100t minus 63.4 degree volt. So that's about it in this video. So all the theorems that you have learned in electric circuit 1, you could apply it in this topic involves complex number. So thank you for your time. Next, we will see in another example which is on superposition. Thank you.